Hi, Bob Sterner here, and in this video I'm going to present the first of several very simple mathematical models of lake loading. We do this exercise not so much because the mathematics is that important by itself, but because exploring this concept thoroughly, quantitatively, and precisely like you can with a mathematical model will greatly enhance our understanding of the principles involved in lake loading and how we manage lakes for water quality. We're going to start with a lake, which we represent by a box. There's our box, which is our lake. And this lake has fixed volume V. And we're using the units meters cubed in this case for volume. This lake has one inflow and one outflow. With fixed volume V, the hydrologic flux in must equal the hydrologic flux out. So we'll use the symbol Q for flux of water, meters cubed per second. And another assumption we're going to make about this lake is that its contents are completely and instantaneously mixed, meaning the concentration of substances at any one moment anywhere in the lake is identical. We're going to pay attention to two concentrations in this model. We have the concentration of substances in the inflow. This is essentially our loading, which is what we're interested in here today. So Ci is the concentration in the inflow with units moles per cubic meter. And the concentration that we're ultimately most interested in is the concentration of substances in the lake. We represent that with the symbol C, also moles per cubic meter. Now, the assumption of complete and instantaneous mixing also means that the concentration of solute in the outflow will equal the concentration in the lake. So the concentration in the outflow is also given by C. So that's our complete description of this very, very simple lake. One inflow, one outflow, complete mixing. Now that we have our first very simple model of lake loading, let's see what that model has to teach us. The first thing we need to do is recognize that the quantity, the mass of substances within the lake will be given by its concentration in moles per cubic meter times the lake volume in cubic meters, giving the units moles. And what we want to do is ask how that mass of substance in the lake varies with time, or rather, what is the time derivative of dCV dt? The time derivative of the quantity of substances within the lake will be given by the rate of inputs, which is given by the concentration in the inputs times the hydrologic flux Q. This quantity also has units moles per time, as does the time derivative on the left of the equal sign, minus the outputs, which is given by CQ, the lake concentration, which is equal to the outflow concentration, times that hydrologic flux Q. So now you may recognize that what we have written here, dCV dt, is a product of two quantities, C and V. And you may remember the product rule from calculus. And if you do, then you may also recognize that because we have said the volume V is fixed, and therefore its time derivative is 0, then the thing that we have just written for dCV dt will also be equal to dC dt times V. Now, the easiest thing that we can do, and the most illustrative thing we can do with this model at this point, is to solve for steady state. At steady state, dC dt becomes 0, and so this term becomes 0, and therefore 0 equals CIQ minus CQ, again at steady state. We can then do a little algebra. So Q times the quantity of Ci minus C is equal to 0, and this thing on the right of the equal sign will equal 0 only when Ci equals C. So this very simple loading one model, one input, one output, complete mixing, says that given enough time so that the model reaches steady state, the concentration of substance in the lake, C, will come to equal the concentration of stuff in the inflow, Ci. So over time, concentration versus time, where concentration in the inflow is there, if we start with a lake with low substance concentration and let the model run, over time the concentration in the lake will grow until it approaches, but never quite equals, the concentration Ci. Likewise, if we start with very high concentration C and let the model run, basically lake concentration dilutes out and approaches Ci from above. So this model is presented in this case because it's a good benchmark for us. It's not necessarily a good model of how lakes work. In fact, as we will learn through this lesson, concentrations in lakes seldom equal concentrations in the inflow, but it's a good starting point for us. So that's the end of this video clip explaining our loading one model, and I hope you had a good time watching it, and we'll talk to you soon. Bye.